we were just looking at the distribution for a hidden Markov model. And remember, the picture to always keep in your head for a hidden Markov model is this trellis diagram. And you can think of, so we looked at this little example with the handwriting recognition. This is so cool. This works so well. It's amazing. Trellis. Let's see if it'll get this. Oops. If I try to confuse it and write, make mistakes in my writing. And it still got it. Look at that. Tell us, can we add something? Trellis diagrams are cool. That is so neat. So in that sort of little example, each of the hidden states was the abstract letter, and the observed thing was the sort of, how I wrote the letter. And I'm not sure if they use that, but if they use hidden Markov models, but they might use hidden Markov models for that, and you certainly could use a hidden Markov model. Probably would work well. So now we were just about to write down. So we wrote down the joint distribution for the general thing, and then we said, what these parameters are, and just to make it concrete, let's write down the joint distribution in terms of these parameters. So we have pi I times the probability, well, it's the probability of x1 given z1, so this is going to be epsilon z1 of x1 times the product as k goes from 2 to n of the probability, the transition probability, so it's t of, what's the first one? The first one is zk to z, is it zk or zk minus 1? Zk minus 1, sorry. Zk minus 1 to zk. And then we have the emission probability, epsilon zk xk. So it's the probability that that in state zk we emit the value xk. So the probability of transitioning from zk minus 1, from the state the hidden state zk minus 1 to the hidden state zk, and so on. So let's see, did we get that right? Is that right? Let's see. We got the initial distribution, the first emission, k minus 1 to k. Yep. So that's the joint distribution in terms of these parameters. Okay. So this t I sort of mentioned. This t, let me just write it down here. This is called the transition matrix, if you hear that terminology. So it's the matrix where the ijth entry is tij. And let me make a remark about what you might choose for these emission probabilities. So this is just a remark here. Remark. What you could choose for the emission probabilities. The emission probabilities can be pretty much arbitrary. Pretty much arbitrary. And, for example, you could choose these to be discrete. These x's could take discrete values. That's certainly one possibility. Another possibility, they could be real numbers. They could be real valued. And so you could have, so if they were discrete, you might choose, if they took values in a finite set, then you would just have some PMF. If they took values in some countably infinite set, you could choose one of the, like a geometric distribution or some other distribution on, or Poisson or something like that. If they were real valued, oftentimes people use, it's a very common choice for real value to use Gaussian distributions for the emission probability distributions. But of course, you always want to choose the distribution that makes the most sense for your particular application. And they could be something higher dimensional, right? Like in the, maybe, in the handwriting example, there would be some higher dimensional thing where you actually get a point in a high dimensional space, like the picture, like the actual, image of a letter, Q, something like that. So it would actually be that whole image. So these are pretty much arbitrary. The main thing is here, the main thing that makes the hidden Markov model work is not the form of the distributions that you choose. See, that's something which is a little bit different. Earlier models, like we talked about, especially, for example, in the Bayesian naive Bayes model and in the Bayesian linear regression model that we talked about, the form of the probability distributions, the fact that they were, that we used conjugate priors and everything. Well, of course, I mean, those were Bayesian examples. Here, we're not really being Bayesian or anything, I guess. But the form of the distributions, the point I'm trying to make, is that the form of those distributions was extremely important to making them actually work. And here, the form of the distributions, I mean, at least the form of the individual parts, is not as important as the fact that the distribution factors in this way. This is the key thing. This factorization, the fact that it respects this graphical model, is the key thing that makes the hidden Markov model work. And by work, I mean that you can actually do tractable inference in the hidden Markov model. And in a video or in a couple videos sometime very soon, we're going to talk about how to do that inference. The sort of engine that drives the hidden Markov model is the inference algorithm, and the fundamental part of it is what's called the forward-backward algorithm. So we're going to take a look at that. And now let me just give you one more little example here. One more little example. Something that you could... So this would be an example of data that you could think about as being actually explicitly generated by a hidden Markov model of that form above. So suppose that the xi's, or rather the zi's, suppose that z, or zk, I guess, zk takes values in -1 or 1. Take this as our finite set. I used 1 to m before, but the important thing is just that it's a finite set. And let's take the x's to be real numbers. And let's say that the z's sort of flip and flop back and forth. So let's make this is -1. This is 1. And let's say, so if z starts out here, I guess we need to put ticks on our axis. Maybe it's really fine. Actually, let me not put... Let's say it's just so super fine ticks on this time axis. It has to be discrete, of course. But suppose it's some super fine grid here. And the z's, I'll draw the z's, I guess, in red. The z's tend to stay at the same value, and then they maybe going along here, and then it flips. And it tends to stay here for a long time, and then it flips. Right? So the z's are doing something like this. So it's sort of sticky. It tends to stick at the same state. And you could easily write down a transition matrix for that. So T would be something like, 0.99, 0.99, 0.01, 0.01, something like this. So the probability that you stay in the same state is very high, and the probability that you switch. It doesn't have to be a symmetric matrix. All it has to be is that it has to be a stochastic matrix, because the probability of going from I, so this would be like I equals 1, this would be like j. The rows have to sum to 1, because this has to be a probability distribution over all the possible j's that you might go to. So we could also, I mean, this could be like 0.02 or something here. Okay, so let's say that that's our z's. And then what are the x's? Let's actually make the x's in a different color. X. well, maybe not green, if in case you're colorblind. Let's make them in blue. xk in R. And the x's, let's say that the x's are normally distributed about the z's. Normally distributed about the z's. So maybe it's something like this, with some, maybe some small, sort of small variance here. So you get these x's, or these xk's. And each of these values depends only on the x or the z, conditioned on zk. Xk depends on, it's drawn only, it's conditionally independent of everything else given zk. That's what the model says, right? That's what the model says. Conditioned on zk, xk is conditionally independent of everything else. And you can check that. Actually, that might be a good thing to check. You can check that using the d-separation property, the d-separation theorem. So these are just these, whoops, Gaussian distributed things. And so if you have data like that looks like this, then the HMM might be a good sort of model to use. Okay, so hopefully this is a good an illustration for you to sort of a concrete example for you to visualize how, what these parameters are doing and how you might, what data generated from an HMM, in this sort of very, very special, this particular case for this type of choice of parameters, what it looks like and how you might choose the parameters for an HMM. Okay, so that's hidden Markov models. That's what they are, sort of just the definition. And next, we're going to look at the forward-backward algorithm for doing inference in the hidden Markov model. And that's going to be cool. It's a fantastic example of dynamic programming. So we're going to take a look at that next.